Hello and welcome to today's lecture. So, in the last class we had introduced the student's t-test for small samples. So, for small samples you can no longer use the z statistics, but you use the t distribution. Okay. You use the student's t distribution. So, this is called the student's, was also referred to as student's t-test. Okay. This was introduced by Gossett in 1908. So, what you do is you calculate the t statistics given by this expression, okay, and what you will find, okay, compared to the normal distribution, the t distribution is much more flatter. Okay. But as your n increases, the t distribution approaches the normal distribution. So, this is your t and this is your normal, okay, normal distribution. Okay. And just like for the normal distribution, you had one tailed or two tailed test. Okay. For the t distribution, also you have either one tailed or two tailed test. Okay. Here, as before, you calculate. So, this is your t of alpha, where alpha is the area under this curve, okay, and your hypothesis is mu equal to mu naught and H A is mu is greater than mu naught. For the two tailed test, okay, you have two tails. However, please note for the t table, okay, it only gives for the upper half, which means if I want to calculate this alpha, okay, if this is my alpha prime, let us say, okay, I have to set 2 alpha prime equal to alpha. Okay. So, let us take a sample example. So, let me again assert. So, your t table, okay, t table only provides the values, okay, it only provides the values, of t corresponding to upper tail areas only. Okay. So, let us take an example to see it. Okay. So, imagine, so it is estimated the average house or family consumes 350 gallons of water per day, Okay. So, you have taken a sample, a small sample of 20 randomly selected families. Okay. And for these 20, you have calculated a mean x bar of 353.8 and S of 21.85. Okay. So, the question is, does the data contradict the assumption? Okay. So, you have your H naught is mu equal to 350, your H A is mu naught equal to 350. Okay. So, I can calculate my d f is n minus 1 is the degrees of freedom equal to 19, okay, and the value of t is 353.8 minus 350 by 21.85 divided by root of 20 is approximately 0.78. Okay. And corresponding to, okay, so corresponding to df equal to 19 and alpha equal to 0.05. So, you can find out T of alpha is 1.73. Okay. So, since 0.78 is less than T of alpha, hence I can accept H naught. So, for calculating the p value, I have to write it as 2 of probability of t greater than 0.78. Why this 2? Because I only get the upper tail information from a t table. Okay. So, this comes out to be 0.45. Okay. This again asserts that this difference is not statistically significant. Okay. So, using a t test, I can do population difference, okay, between population means okay. So, how do I do it? Okay, you know that I can calculate. So, for large samples, for large samples, you calculate the test statistic as x1 bar minus x2 bar minus of mu1 minus mu2 by root of s1 square by n1 plus s2 square by n2. Now, what is known is this test statistic for small samples does not follow normal distribution. One, and secondly, it does not follow T distribution. So, the only way to make use of T distribution is to make one particular assumption that both the populations have identical. So, this is the assumption. Assume. So, if you assume that both the populations have identical sigmas, that is sigma 1 equal to sigma 2, okay, then you can calculate the T statistic. Okay. In that case, you can calculate the T statistic as x1 bar minus x2 bar minus of mu1 minus mu2 by root of s square into 1 by n1 plus 1 by n2. Okay. So, because your population standard deviations are same, you assume similar standard deviations for both the samples. Okay. So, this for calculating the t statistic, I need to calculate df and I need to calculate s. Okay. So, how do I do it? So, you estimate the sample standard deviation using the following expression. Okay. And you set df equal to n1 plus n2 minus 2. Okay. So, n1 minus 1 into s1 square will give you the population, the sample variance, same for the sample variance for this, and then you average it by n1 plus n2 minus 2 to estimate the average sample variance for both the samples. Okay. Okay. So, let us take an example. So, imagine an examiner wants to assess whether students would perform similarly or differently if the exam was online versus if the exam was classroom. So, here the exam is held in the classroom, here the exam is online, and he has chosen n equal to 9 samples for both of them. So, he has taken 9 students who have taken online exam and 9 students who have taken classroom exam. So, their marks are as follows. And we want to know whether the performance of students taking the online exam is identical or different than those when they give the classroom exam. So, my null hypothesis is mu1 equal to mu2, and my alternative hypothesis is mu1, let us say, greater than mu2. So, we have to what do we assume? We have to assume that populations, that the sampled populations have same variance. So, with this assumption I can calculate. So, for this I can calculate x1 bar as 35.22 and S1 as 4.944. For this population, accordingly I can calculate x2 bar as 31.56 and S2 as 4.475. Now, using this expression, you know N1 and N2 both of them are 9 as per this expression. You have calculated S1 and S2. So, you want to calculate S. So, using this expression you will get S square equal to 22.236, and for a significance level of 0.05, for alpha equal to 0.05, you will calculate T of, so S square is 22.236 and T is 1.65. So, this is what you calculate, and for 5%, 0.05% alpha equal to 0.05, you can calculate T of alpha as 1.746. So, what you can clearly see is because this value is less than this value, I cannot reject H naught. So, I cannot reject H naught. So, I need to increase the sample size in order to say anything about whether the performance remains same or it changes. So, that brings us to a close of our discussions on population mean and doing test of hypothesis for population mean, but in many cases population variance might be more important. Variance is more important. So, for saying anything about whether two samples have same population variance or different population variance, you use the test statistics as something called a chi-square statistics. So, this is chi-square, and chi-square is given by the expression n minus 1 into S square by sigma square. So, S is your sample variance, sigma square is your population variance. And if you plot this, the chi-square curve is asymmetric. So, this is, so chi-square curve looks something like. So, just like any other distribution, you can calculate chi-square according to alpha, where alpha is the area under this curve. So, how does a chi-square table look like? Okay. So, in a chi-square table, you have the following values. Okay. You have df, which is your degrees of freedom, n minus 1, and you have these values provided. Again df. Okay. So, if you want to test your population variance is certain value, so you can have your null hypothesis as sigma square equal to sigma naught square, and you calculate the statistics. Okay. So, your test statistic is chi-square equal to n minus 1 into s square by sigma naught square. For a one-tailed test, okay, for a one-tailed test, okay, so you have to accept. So, your hypothesis is not true if your chi-square is greater than chi-square of alpha. Okay. So, this is your rejection zone or rejection criteria. For a two-tailed test, okay, for okay, so we call it. So, this area is alpha by 2, and this area is alpha by 2 also. Okay. So, for two-tailed chi-square test, okay, so this is two-tailed test. Okay. So, I have these two zones which fall within the rejection zone. Okay. Let us take an example. Okay. So, let us say a cement manufacturer says that average strength of the cement that he makes has a range of 40 kg per centimeter square. Okay. So, to test it, n equal to 10 samples size has been drawn, and based on this you have obtained an x bar value of 312 and an s square value of 195. Okay. So, can we accept the manufacturer's claim? So, what you are given is the range is 40, and you can use the approximation range is approximately equal to 4 times sigma. So, this gives you sigma is equal to 10. So, your null hypothesis is sigma square equal to 100, and your alternate hypothesis is sigma square, let us say, greater than 100. Okay. So, you can calculate the chi-square statistics, which is n minus 1 into s square by sigma square, sigma naught square, okay, which is 1755 by 100, you get a value of 17.55. Now, the chi-square for a degree of freedom of 9, okay, so for df equal to 9 and significance level alpha equal to 0.05, if you look up the table, you get a value of 16.919. Okay. So, what you clearly see is this value, chi-square value, is greater than this threshold. So, this would mean that H naught can be rejected. Okay. Let us take one more example. Okay. So, a student thinks that an instrument has sigma equal to 2. Okay. So, and she has done 3 experiments, 3 measurements, which is led to the values of 4.1, 5.2 and 10.2 respectively. Okay. So, can the students assertion be accepted? Okay. So, what do we do? Our H naught is sigma square equal to 4. Okay. Alternative hypothesis is sigma square not equal to 4. Okay. So, my chi-square value is n minus 1 into h square by sigma square. Okay. This gives you 2 into 10.57 is what you calculate the h square, okay, as by 4 is 5.285. Okay. You get a value of 5.285. Okay. So, for df equal to 2, okay, this value 5.285 falls. So, 5.285 falls between chi-square 0.1 and chi-square 0.05. Okay. Now, since it is a two-tail test, okay, now remember, for a two-tail test, so this area is alpha by 2, this area is alpha by 2. Okay. So, chi-square 1 minus alpha by 2 and chi-square alpha by 2. Okay. So, I can say that this p value that I calculated, okay, that 0.05 less than half of p value, less than 0.1. Why? Because this value falls within pi square of 0.1 and chi square of 0.25, but this range, so this half is only giving you half of the total p value. So, the total p value ranges between 0.1 and 0.2. This implies that I cannot accept. So, my p value is greater than 0.1, implying I cannot accept. Okay. You can also calculate the 90% confidence interval. Okay. You can calculate the 90% confidence interval. Okay. Which is given by, okay, okay. So, for alpha by 2 equal to 0.05, chi square of 1 minus alpha by 2 equal to chi square of 0.95. Okay. So, for alpha by 2 I can have chi square of alpha by 2 as 5.99, okay, and chi square 1 minus half is chi square of 0.91 equal to 0.1. So, this if I plug in the values here, okay, what I get is a range between, okay, you can plug in the values 2 into 10.57 by 5.99 less than sigma square less than 2 into 10.57 by 0.1. This gives me a range 3.53 less than sigma square less than 206.07. Okay. So, what you clearly see is this variance sigma square has a wide range. This tells you that based on 3 measurements, you really cannot say whether your standard deviation is 2 or not. Okay. With that, I conclude our class for today, and today we had briefly discussed about how you can do the student's t-test. Okay. Briefly taken a call on student's t-test using the test statistics T, which we found that for small sample sizes, okay, it deviates from the normal distribution, but for large sample sizes you will get the same result. And then towards the later half, we discussed about how we can calculate chi-square statistics to measure population variance. With that, I thank you for your attention.